Welcome to lecture 36 of Industrial Mathematics and Computation. So today we are going to study the modeling of vibrations that will lead us to Bessel functions. But let's first start out with our model of a partial differential equation, which is known as the wave equation. So we will apply this wave equation in polar coordinates to model what happens when you strike a circular drum. The method of separation of variables, which we first encountered on the heat equation, which we first applied to the heat equation, will also be applied here. So that will be then the third example of this important technique. So the functions that we will consider are in a way very classical, but also more special than the sine functions that we have considered before. But the main idea of the application of orthogonality is the same. So as you can see, I have 51 slides. That's mainly because at the fourth part of this lecture, I will very briefly browse through all the topics for industrial projects that we have encountered so far in this part of the course. So we are closing off the chapter on partial differential equations. Before that, we studied control, frequency domain methods in general, feedback as well, and before that we had ordinary differential equations. Okay, so what is our problem? What do we study? We study a model of vibrations for which the wave equation is one of the typical equations. So we have the second derivative with respect to time, so see here time, and at the right we have the Laplacian. The Laplacian in one dimension simplifies to the second partial derivative with respect to space. In this very simple example, we consider a line segment, an interval for x between 0 and 1, and we imagine that this 0, 1 is the space for a string, and at time 0 we pluck the string, so we lift the string up and then we let it loose. A little bit more similar problem like the pendulum, where we have an initial deviation, but there it was only one angle. Here we have an entire profile. So even for one variable problems, you see the distributed nature of partial differential equations. So we have the initial conditions, two of them, and we have also two boundary conditions, which for this example here states that at the endpoints the string is fixed at the left end for x equals 0 and at the right end. So this is a nice problem, and in a way we've studied this problem in numerical analysis. So a word of caution here: applying the method of separation of variables here does not lead to a good solution. So it's a weak solution. So numerical techniques like finite differences are recommended here. Okay, so we have studied traveling waves, and one can use the method of characteristic lines to show that the sum of two functions is a solution of this one-dimensional wave equation, where the constant c is the wave speed. So the wave speed occurs in as a power, as a square, so that makes the squares rather symmetrical, but that's not the reason why. There are very good reasons why we put the c to the power 2, as was explained in numerical analysis. Okay, so verify this. So we encountered the characteristic curves when we studied traffic flow. Here with studying waves, this method of looking at partial differential equations has certainly also its merit. Okay, but what we will consider today is a application of the separation of variables in polar coordinates. So we mentioned polar coordinates before, but we never really got to it. Well, this lecture is where we are going from rectangular to polar coordinates. And why is this important here? Well, we look at the circular drums. Most drums that you see are actually, as music instruments, are actually circular. Then the model here, so the problem that we consider is that we strike the drum right at its center, and because of this positioning of the strike, everything will be symmetric. So we can immediately reduce this two-dimensional problem to a one-dimensional problem. So in polar coordinates, we have a radius and we have an angle. So the radius is the distance from the origin, and the angle is the distance from the horizontal axis. That uniquely characterizes any point on that circular drum. But here, since this is radially symmetric, the angle really doesn't matter. So we forget about the angle. So we have a problem then in two variables. Time, of course, is important. And then we have the distance from the center of the drum. Okay, one dimension in space, one dimension in time. So let us now consider the wave equation in polar coordinates. I glossed over it, but let me now precisely state what we want to know. We want to know at any time what is the status of the membrane that covers the drum. So when we strike it, before we strike it, everything is at level 0. When we strike it at the center, there are vibrations. We want to model those vibrations. So we are going to solve the wave equation in polar coordinates. So you see the Laplacian is very convenient now. It's still the same equation, and it's only here that we specify that r is between 0 and 1. So we also don't have a wave speed, so everything is with idealized numbers. So the radius of the drum is 1. So we have initial conditions. So there is the initial profile, how we strike the drum. So at t equals 0, we have a shape, a given function, in the distance away from the center. We have the first derivative that is 0. We strike only once, so that means that just like with the pendulum, we had an initial deviation in the angle and then we let it loose. So we strike the drum and then we don't touch the drum anymore. We just listen to the vibrations. There is a boundary condition, so at the edges of the drum there is nothing moving. So at r equals 1, at all time the drum is fixed there. So at this point I should mention that only 3 conditions. With the wave equation earlier, we had 2 initial conditions and 2 boundary conditions. It appears that 1 condition is missing, but as we will reformulate this problem, it will become clear how we can fill in the fourth condition. So don't worry, it will all turn out well. Okay, what is the method that we apply? We assume that we can decompose our solution in a part that depends only on space and a part that depends only on time. So we have two functions. One depends on the distance from the origin, so that's from the center, so the origin is the center of the drum. So there is the capital R depending on the little r, and the capital T depends on the little t. Okay, so the separation in variables, the separation of the variables then leads to two equations. So in some sense, it doesn't seem like it gets any simpler at this point. We started out with a very compact notation, and now we have two equations. So the problem seems to grow. But then comes the key. So as we are separating the variables, so we have derived two equations. We can, if we bring everything, if we separate, so we have, what do we have? Very important, we have the wave equation, which consists of the derivative with respect to time equals the Laplacian. So the wave equation is equaling the left sides. So we take the right sides, and that gives us the new single equation. We regroup the terms. At the left, we have only that depends in time, and at the right, we have only that depends on space. Again, if one looks at this equation now, it looks a little bit tidied up. We have the left depending only on time and the right depending only on space. And indeed, we had that already. So the format was already in a good form. However, now the key implication of this assumption is that if the left only depends on time and not on space, and if the right only depends on space and not on time, that means that there is a separation constant. So we have then a constant independent of time, independent of space, that we can wedge in to this equation. So there is the purely algebraic justification to make it simpler, but then there is the very important implication that leads to this separation constant. So, and we are using lambda as the natural and conventional symbol for an eigenvalue. So we will have eigenvalues and eigenfunctions. Okay, so here we go. We have again the main implication of the method of separation of variables, leading to two decoupled ordinary differential equations. So we see them here. Thus far, the polar coordinates have not really come in, but we only delayed. So what is now this Laplacian in polar coordinates? So that's the key question now. Okay, so if you have done your homework, then it is a homework exercise. A little bit tedious, but if you work in a very systematic way, so here what I try to do on this slide, I have the Laplacian in rectangular coordinates. I give this explicitly on with the x and the y, and then I have the Laplacian in polar coordinates with r and theta. if you make the exercise, please consistently with every partial derivative, with not only with the Laplacian here but also to the right, indicate explicitly the independent variables. And remember the chain rule. So in a way, it is disciplined symbolic work, and I think a computer algebra system will help you there, and knowing what you need to obtain. So the final result, so you will have expressions, well, as always is the case when you do symbolic computation, but then in the end there is a happy ending there. So everything collapses using the standard identity cosine square plus sine square. Okay, so nevertheless, the Laplacian in polar coordinates is a little bit more complicated. So we have this division by r. So r actually should not be 0. So that's kind of at the center in this drum. We kind of have a problem here. But in our case, we actually got rid of the theta. So it actually get a little bit simpler. So the r is actually independent of theta because of this symmetry in our problem. So we have then an expression for the Laplacian, and we also have then our second ordinary differential equation in space. Two second order differential equations. Okay, it's time. So it's time to indicate what is alpha, what is lambda. Here is the natural solution, and in some sense we have seen this derivation already earlier on, but then we did it for the heat equation, and then we used x and the t was the little x. So in symbols, this is just changing the symbols. We we replace the lambda by minus alpha square. And why do we do this? Well, look at the solution that we expect. In time, we expect some fluctuations. So we have a linear combination of a cosine and a sine function. If we are working with alpha square and minus alpha square, then it works out very neatly. So the proposed linear combination of a cosine and sine function, where alpha occurs in the in the frequency, in the frequency of the sine and the cosine, then by the chain rule we have the minus alpha square coming up. Okay, so one of the components in the separation of variables, so the piece that depends on time, is a very nice combination of a cosine and a sine. Okay, so this is explained here purely symbolically and algebraically, so what lambda is. There is another exercise which we encountered in an earlier lecture, which goes a little bit harder. So that's truly a harder exercise that asks you to show and to verify that the eigenvalues of the Laplacian with zero boundary conditions, that they're all negative. So alpha square is a positive number, minus alpha is a negative number. So we all have negative eigenvalues. So there is a geometric, so there's a purely algebraic justification what lambda is, why we write it the way we do, but there is a deeper reasoning here. Okay, We can still simplify. So we had one of our initial conditions, so we strike only once. So the derivative with respect to time is 0 at t equals 0. So we take the derivative with respect to time and we plug in t equals 0. Support that we do this in this order, not the other way around. So when we plug in t equals 0 in the derivative, the sign at t0 is 0. The cosine at 0 is 1. So we must have that the derivative at 0 is 0, thus b equals 0. So our function in time becomes then very simple. It's just a function that is a cosine with a frequency containing the alpha and then a constant a. Now, of course, with partial differential equation, we just don't have one solution, but we will have infinitely many. So the decoupling helps us only a little bit. Okay, we dealt with space. No, we dealt with time. Let's now looking in space. So we are solving the wave equation in polar coordinates. Now we are going to make a substitution. So we have the alpha square that is sitting in there. We're going over to, so we multiply by r square. Why do we do this? Well, we also multiply then potentially by 0, so r should actually not be 0. But you see that r square alpha square gets in there. Now, if we replace r by z over alpha, then here in this term, we have only z left, or z square. Now, if we do this also, so I should have done this a little bit more pedantically. So the partial derivatives are functions in R. If we are substituting, replacing R by z over alpha, then actually the 1 over alpha appears in the um, partial derivatives. So there is the r that appears here from the alpha, and then there is the 1 over alpha that appears by replacing r by z over alpha. So the main point is that in the partial derivatives, because of the chain rule, that the alphas drop out. And then we have a much more simpler ordinary differential equation, only depending on z. Okay, so how do we solve this now? Well, it turns out that we don't really solve the equation in the classical sense. There are functions that are defined to be the solution of this equation. So this equation is called the Bessel equation, and the solutions are called the Bessel functions. So there is a one-to-one correspondence between these functions that are actually defined as the solutions of this equation. So in a way, it's kind of circular. We are solving this equation by saying that these are the solutions. And this is a second order equation. We will have two functions, two types of Bessel functions. They are called the first kind and the second kind. So these Bessel functions are very well known, so they're still regarded as special, but they are immediately available in SymPy, and they're also available through the package special functions in Julia. So here is the verification in SymPy. We import the Bessel J and the Bessel Y. Bessel J first kind, Bessel Y second kind. So in our application, we only need the J naught and the Y naught. So the Bessel functions depend on a parameter, which can be a complex number. Um, Here we verify that when we compute the two derivatives, first derivative, second derivative, then set up the equation for the ordinary differential equation. It's complicated if you look at it, but when you simplify, it simplifies to zero. So SymPy knows this property from the Bessel functions. And likewise for the Bessel function of the second kind, purely formally. And you can argue, well, that doesn't really help us. So we just have a formal solution here. But they are proper functions, so we can plot them. So here I'm going a little bit too fast. If you would solve the Bessel equation by SymPy, and you can do this, then you would see a power series. And the power series, you can actually use this to evaluate the Bessel function. You should take sufficiently many terms. So that is one way to see the power series expansion. We're going rather fast here. With this plot, it is kind of I wouldn't say obvious, but it becomes clear why these Bessel functions are actually very good at modeling vibrations. So we have the peak vibration at the origin, and then farther away towards the edges of the drum, they kind of damp out. So that is the geometry of the vibration. So this is one plausible solution to this model. Here is another one. So this is the Bessel function of the second kind, the y. You also have this phenomena that you have this kind of oscillation. So the vibration, the shape, the profile of the vibration. But the second kind is something that we will not be using because it's probably not that clear from the picture here, but and that's because of the granularity of my plot. If my granularity of the plot would be smaller, and that could be an exercise for you to figure this out. If you plot closer to zero using a very tiny step size, you will see that the -3 actually, the lowest value that is plotted, actually goes down and down. So the function of Bessel function of the second kind is no longer bounded. And that contradicts our assumption. So we only had 3 assumptions, but we will throw away the Bessel function of the second kind using the bounded nature of our solution. Okay. This slide here essentially states what I just said. So we have this initial condition where we have a bounded function everywhere. So we have a bounded profile. So we will work only with the Bessel functions of the first kind, not those of the second kind. Okay, let's now impose the boundary condition. We have already used one condition, the second initial condition is already used. Let's now use the boundary condition that at r equals 1, so at the edges of the drum, there are no vibrations, everything is fixed. Note that this is spatial, constraint. But nevertheless, let's look at the entire solution, the product of the capital T with the little with the capital R, and there's a typo here. The capital R depends only on R, so I still have to fix this. But here it is fixed. We have the shape of the function. So it's a function in R and T. So in the boundary condition, T can still be anything, but R is now 1. And that means that the T can still be anything. So we have the A cosine alpha T that cannot be 0 everywhere for any time. That would give a trivial solution. So then we are left with the condition on alpha. And what does this mean? So perhaps you have been asking already all along, what is this alpha now? Well, this is what alpha is. Alpha is a root of the Bessel function. And it turns out we have infinitely many. So we have plenty of roots. Great. Okay, we are half hour in, and we have essentially almost solved this problem. It looks very abstract with the Bessel functions, but here note that getting the roots of the Bessel function is actually very straightforward. So at least if you use this fast Gauss quadrature, and if you're using Julia, so computing the first 10 roots for J naught is just one instruction. You see that these values actually also are growing. And again, they are the roots in space, but if I go back, they're also here the frequencies of the cosines. So our solution, and we can still talk about the solution, so we have not used all the conditions yet. So in the solution we have the roots geometrically of the Bessel function, but these roots appear in the frequencies of the cosine. So the shape of the solution, it's a little bit similar to what we did with the Fourier analysis, where we were writing a signal as sine functions of increasing amplitude, increasing frequencies, and with different amplitudes. We're going to do the same here. So in a way, there's a lot of material that comes at us again, but we've seen this before. So the letters are different. We have now, instead of sines, we have cosines, and we are separating differently in space and in time with polar coordinates. But the more things are different, the more actually they are the same. Okay, we are lucky to be using Julia, where everything is readily available to us. So we can make and available for free. Let us look at now the roots of these Bessel functions. So take the first 5 Bessel functions and plot them, and see then what happens about the roots. So here the parameter n is an integer, but in the roots one could have given, so we gave 0.0 for the zeroth Bessel function. These Bessel functions of the first kind solve a more general Bessel equation. So this problem can be made more general with a parametric expression for a parameter, and the parameter is n, but sometimes this is also called a continuous variable, so one uses nu in the special functions documentation in the Julia package. Okay, I told the solution already, so here it is. So we have now infinitely many, as many as we like, solutions. And they are parameterized by these eigenvalues. Or rather, the root squared and then taking the negative are actually the eigenvalues. So these are the eigenfunctions, the u subscript n are actually the eigenfunctions. They are parameterized by the roots of the Bessel functions. Okay, so we have infinitely many, so which one to pick? Well, we choose all of them and sum them all up. So if we have one solution, so that's because of the property of the derivative, which is a linear operator. So then any linear combination is actually also a solution. So here we have the general form of the solution. One can actually not say the solution because I'm still using the capital U to indicate that is one solution living under the assumption of the separation of variables, also with the assumption that we strike the drum exactly in the middle. So this is all very idealized. We haven't used yet, so there are parameters in there. The A's, the amplitudes of the cosine, still need to be determined. And for that, we use the initial condition that we have a given profile. So in a numerical example, you would need to give a profile. So I'll leave this off here. Orthogonality. So in a way, this is an approximation problem now. So it's a problem where we are going to compute a least square approximation, exploiting the orthogonality of the Bessel functions of the first kind. So we have a special inner product suitable for polar coordinates that will essentially solve our problem. So again, we are making a lot of steps here. I leave it as an exercise, so it's a numerical analysis exercise. Apply a numerical integrator to verify that the Bessel functions are indeed orthogonal using the parameterized by n, which is a discrete parameter, where n is the root, corresponds to a root of the Bessel function. So you can use a black box numerical integrator that should suffice, hopefully, to verify the orthogonality condition for the first 5 Bessel functions of the first kind. Okay, the inner product, and I skipped over it. So we have the beginning of the slide, which states our problem. So we have the initial condition at time equals 0, where we have an initial profile. So if you solve this, so one can say, look, my initial profile is actually the Bessel function. Then, so one can skip this orthogonality part by assuming the Bessel function as a suitable profile. So then you know immediately that you only use a1 equal to 1. All right, but in general, you can use any profile, and the exploitation of the orthogonality means that in the infinite sum, that when you take the inner product with the mth Bessel function of the first kind, that only n equals m survives in this infinite sum. So doing this for an infinite sum takes forever, but we know the orthogonality property that only one term remains. And that leads us then to an integral formula for the coefficients. And that essentially solves the problem. Okay, I'm 40 minutes in. One last exercise. So what happens if you would do this on a square drum? So the book, our textbook, proposes this as a solution. You see now that the Fourier analysis comes in again. So the signs, we have increasing signs of increasing amplitudes, increasing frequencies. But now it's a two-dimensional problem. So we have a double sum. So look at this problem. There are three parts in this. First, set up the wave equation that needs to be solved. Specify the initial and the boundary conditions for the square drum. Again, assuming that at the edges everything is fixed. Then you have a given profile, and the coefficients should arise from the Fourier series. I'm trying to explain here part 3 already, so you can immediately go to part 3. So part 3 is redoing the separation of variables, but now you do this, the space now has a two-dimensional problem. So you will have a function in two variables x and y, separated from time. But you see again the cosine getting in there. Okay, so important is that sines, they are periodic. We have now the increasing frequencies both in the cosines and both in the sine functions. So that makes for a plausible proposal. Solving part 2 means that you could just make a plot of the first term and idealize everything, assuming that for the first term you have m equals 1, n equals 1, you have the c coefficient also equal 1, and just plot it, and you will see the waves going up and down. Okay, can you hear the shape of a drum? So that was a title for a paper published in the American Mathematical Monthly. So the purpose of this lecture, and of actually our entire course, is that you would have access to the literature. So the American Mathematical Monthly is published by the Mathematical Association of America, with a heavy focus on education. So the American Mathematical Monthly articles are meant to be readable for a very broad audience of mathematicians, and one would say everybody who is mathematically literate, which is everybody in this course here. So the textbook has this as a project, suggesting that the answer to the question is no, you can't hear it. But according to a more recent paper, so our textbook is published, the versions before 2011. So a more recent paper using the Schrödinger equation states essentially that this problem is still open. So what is the purpose of this proposal for a project? And by the way, this is project number 18. I will very briefly scroll through the list in the remainder of this video just to make this video also self-contained. But let me dwell a little bit longer on this project. So in some sense, this lecture was mainly focusing on the mathematics, and a little bit on the computational sides as well. So the industry fell out. One can argue that beating a drum is actually not really things that people do in an industry. But the main point of the topic for this project is actually that you figure out why this is an important problem in industry. Um, so in various areas, that one is very much that the solution to this problem is very important. So there is also the mathematical side. The Schrödinger equation is one of the important equations for which we didn't have time in this limited series of lectures. So this project could make up for this. So in summarizing the findings of the two papers, you could see how well you can understand what is presented there given the background that we have covered in the lectures. All right, that leads me to conclude. We studied Laplacian in polar coordinates to model vibrations in a circular drum. This is problem 5 in chapter 11 in our textbook. So we studied the heat equation, traffic flow, diffusion with traffic flow, and today we studied vibrations. So this is a very small subset of what can one do with partial differential equations. Nevertheless, I hope it gives you a taste. Also, that this complements the lectures in numerical analysis, where we were exclusively focusing on the techniques. So, the method of the separation of variables has given us a lot of mileage, but in general, if one wants to study partial differential equations in greater generality, the numerical techniques must be applied as well. This is certainly the case with the wave equation. All right, I now will run through 17 proposals for projects. So the first proposal is regression, but now with logistic model with the carrying capacity, taking the carrying capacity into account. Second project is also modeling a population that now takes the age structure into account. So this is a mathematical biology project from our excursion into ordinary differential equations. We have covered traffic. We have seen this with partial differential equations. We've seen it with frequency domain methods. Here we had the 3-second rule that we can justify with the ordinary differential equations. Project number 3. Oh, here is the 3-second rule, or perhaps not. So there is a relationship between the delay. So if you so the should say that I shouldn't dwell on these projects, but if you ever are participant in a platoon of cars, then this is not stable. Show that that is indeed the case. All right, then frequency domain methods are very frequently applied in engineering. One could say that this is engineering mathematics, but one can explain also social dynamics, the labor market, with feedback. So this is what this project does. Software, we are doing free and open software symbolically, numerically, typically via Julia and the Jupyter Notebook, but there are also other open source software packages available. Skylab is one of them. You might find in the documentation of Skylab this design of an automobile cruise control system, but this problem is worked out in our textbook. Our lectures didn't have time for this, so some of the projects are asking you simply to read the textbook for portions that we skipped and essentially turn a lecture on this topic. Um, we've seen the root locus method. One can build a general root finder for this. We've seen air quality modeling. This goes back to our numerical analysis course. We've seen the condition on the criterion on the step size in time and in space. The heat equation, where does it come from? That's the topic of this project. Population modeling again, but now with the transport equation. Is this a model that makes sense? Here is a variation on the heat equation. So this is one of the problems that we skipped in chapter 11. Work it out. We have the heat equation in polar coordinates, a bit similar to what we studied today, but we've seen the Helmholtz phasor solution method. Apply it to this problem. Least square fitting again. There are various models for traffic flow. We've seen the Green Shields model. Is this a good model? The relations that we've seen there, can we fit? Especially, can you determine the free traffic speed and the jam density? The geothermal heat pumps, again the Helmholtz phasor method. The thickness of walls in a construction, not too thick, not too thin. Helmholtz again. And here we have a biology project. How deep should you dig to find worms? And that's project 17. So project 18 is the project for can you hear the shape of a drum? Okay, I hope this lecture was interesting. I sign off on this because I'm running over time.